Hello. Today AC traction motors are the dominating type of traction motor for most applications. But historically we've had a lot of different kinds of motors as traction motors. This is a list covering all different kinds of motors we've had in history and their application. Initially serially excited DC motors were the common one. For the early DC motor electrifications, this was a typical drive system, simple and straightforward. When converters started to appear in the late 60s and the 70s, it was more common to use separate excited DC motors. So that's the common solution for most converter-fed DC motor drives, both from DC supply for subways and trams, as well as for AC supplies when you have a thyristor rectifier feeding a DC motor. Today there are hardly any new trains developed with this kind of drive, but still there exist a lot of different drives on the market. When it comes to AC traction motors, the history of electrification of railways was a little bit governed by the fact that we have the single-phase AC series motor. And that is, of course, a motor that is similar to the serially excited DC motors, but in this case it can be supplied by an AC. As I think I mentioned before in Chapter 1, this was the typical reason behind the early AC electrification, the fact that this motor couldn't operate at higher frequencies than perhaps a limit of 25 Hertz. So we had to electrify with a low frequency AC. We'll come back to that later. Later on, when converter-fed AC motors started to appear on the market, there was a little bit of a fight between either voltage source converters and induction motors, and on the other hand, converters with a current source type and typically then used with this electric excited synchronous machine. This electric excited synchronous motor is for instance also used a lot in ships for the bow propellers and other heavy applications and high power applications. It's pretty common in France for several types of locomotives, and also some of the generations of the French TGV high-speed train has this electrically excited synchronous machine. During the 80s and 90s, the induction machine itself, the three-phase induction motor, started to appear, and it became the most common traction motor today, and it's totally dominating the market right now, and more or less all new trains being built, and still most of the trains developed have the three-phase induction motor as a propulsion motor. We'll talk about that one in a few minutes. Today we are starting to see new technology appearing on the market. The permanently excited synchronous motor is of course a good candidate. It's been used in a few applications, and it has some benefits compared with the three-phase induction motor, like higher power density, lower losses, a little bit of flexibility when it comes to design. It's been introduced in the market in the last years, and of course the drawback, as we'll see later, is that the cost of magnets is increasing, thus making it doubtful whether it would have a breakthrough or not. Let's now continue with AC motors and typical design and their features. Traction motors today are designed for a high power density. That is a small volume and or weight in relation to output. What is high power density? Well, that is compared with industrial motors. We design traction motors to have a higher power density, because on trains and in other vehicles, the size of the machine, the size of the motor is important. We want to have as high output in as small volume as possible, and that puts a demand on a high power density. Sometimes we can accept perhaps a little bit higher losses to make a bigger motor, or a smaller motor, sorry. The second aspect we have to take into account when it comes to traction motors is that they have to function regardless of loading, because the traction drive itself has features like high speed, low speed, high torque, low torque. It varies all the time. Typical for an industrial motor is the fact that it operates at a pretty constant speed and with a load torque that is varying slowly or very little. So a traction drive itself a traction motor has to adapt to the fact that the traction drive is different compared to a normal industrial motor. It has to be mechanically robust because it's operating in a pretty harsh environment with lots of vibrations and impact from stones, whatever it can be, flying up from the ballast. And it has to be insensitive to dirt and moisture. That is, it has to have a good insulation level. These two equations are fundamental for the understanding of the design of a traction motor more principally. The first one shows the torque, and for people working with electrical motors, the torque itself is often more important than the power level, because torque is what we design the machine for. And you can see that the torque is determined by d square L, and d is the diameter of the air gap of the machine if we're looking at a cylindrical air gap inside the stator. L is the active length of the machine, that is the length of the iron core of the machine. A is the current loading, and B is the flux density in the air gap. The current loading is measured in amps per meter. That is, so to say, a measure of how well you utilize the circumference, the surface of an electrical machine. If you have a lot of conductors in slots, if you can have a high current in each conductor in each slot, you will improve or increase the current loading of the machine. Typical values are in the kiloamps per meter range. And of course, as a manufacturer of this kind of motors, you are aiming at as high value as possible. You don't try to under-design the machine for current loading. Of course, if you do that, the machine will be bigger. But if you overrate it, so to say, if you have too high values of the current loading, you will increase the losses. On the other hand, the second parameter is the flux density in the air gap. So if current loading is the current-driven, flux density is magnetically driven, and that is also determined by physical laws. A typical value is around 0.8, 0.9 Tesla. And of course, if you try to increase that value a lot, you will increase iron core losses, the no-load losses of the machine. So as a manufacturer of traction motors, you normally try to have as high a value of the flux density as possible. So both A and B are electrically and magnetically designing the machine. And of course, normally with as high values as possible. That leaves us at the moment with d square L as the only parameter we can really change. And that is, of course, the volume of the air gap, so cylindrical volume of the air gap. And that means that if you want to increase the torque of the machine, you have to build the bigger machine. There's a straightforward connection between torque and size of the motor. So that, I would say, is a really important conclusion. If you make the machine with the lower current loading and the lower flux density, that will increase the size of the machine physically. So sometimes you can actually find machines which are regarded as high efficiency machines, and they are typically bigger. The second equation relates power to torque. And of course, if you increase the torque, you can reduce the rotation speed, angular speed of the motor for a given power. And on that same side, if you want to have a smaller machine with a lower torque and a lower volume, you can increase the rotation speed to obtain the same power. This is a very important relation. If you want to have more power put into the bogie, you have to increase the rotation speed of the motor. Otherwise, it will be too little space for the motor. And that is also clear tendency today. You can see that traction motors that are typically used for AC traction drives, they might have maximum speeds in the range of 4 or 5, perhaps a little bit higher, 1,000 RPMs per minute. RPMs. That is compared with 15, 20 years ago, more or less a doubling of the maximum speed of the machines. And that is, of course, done in order to obtain lighter motors and to get more power into the same volume. A few words about the single-phase series excited AC traction motor to start with. I will go on with the induction motor, but first give a few examples, a few slides about the single-phase motor. As I mentioned before, it's typically like a series excited DC motor, has laminated poles compared with a DC motor that doesn't have to have laminated poles. Due to the induced voltages in the commutating coil, its operating frequency is limited to 25 Hertz or even below 25 Hertz. So that is, of course, electrically you can design the machine to operate also at other frequencies, but at frequencies about 25 Hertz, these induced voltages will be too annoying. It's designed typically for a low operating speed, 800-900 RPM, that range, which makes the motor very heavy and bulky for a given power. Although the machine itself is interesting because it has a simple control. This is an example of a control of this kind of single-phase AC traction motors. There are different solutions, but this is one of them. It shows the secondary side, secondary winding of a main transformer of the locomotive. It shows that you have different taps here. You can have some kind of output at 334 volt, at 258 volt, 182 volt, and so on. By using contactors, we can connect different parts of the winding to this regulating transformer, and the output voltage will be given by the number of connected contactors. As you can see, we can get different voltages. This is typically, 91 volts, 136 volts, and so on. What's a little bit amazing is the fact that we only get 8 different output voltages. And this is, of course, one of the drawbacks with the old technology of that time. It means that the driver, him or herself, was forced to do all the addition control by choosing any of these 8 different notches. And of course, you can realize that there are pretty big differences between 296 volts or 271 volts and so on. To get a good, accurate addition control is, of course, difficult with this kind of manual control. To summarize these characteristics, these are the changes in speed to current and in torque to speed as you do different control actions in this simple single-phase AC traction motor. So you can see that we increase the power by adding voltage, because this is more or less the torque to speed, the tractive effort diagram of the train. So that is end of part 1 of this lecture.